Hello all, this is Gautam Kumar representing Group 18. Here are my team members, Pratima Samineni, Gautam Kumar Nalluri, Murali Krishna Bomseti. Today we are going to discuss about two research papers. One is learning real-time A-star path planner for unnamed air vehicle target sensing. Another one is simple sub-goaling for research time. So next slide. Here are the few important topics we are going to discuss in this research paper. First one is path planning approach. Can you go back to next slide? Sorry, go to next slide. So here, what is path planning? Path planning is the means by which autonomous vehicles plan ahead their movements and navigate through the environment. A-star algorithm is the pathfinding algorithm that looks for the shortest path between the starting and the ending states. It utilizes the variety of applications. It is used in a variety of applications like maps. The A-star method is used in the maps to find the shortest distance between a source and a destination. Path planning will be effective only when targets are located apart. When the targets are close together, the traditional path planning algorithm is not suited well. Even there are few limitations for implementing it in autonomous fixed-wing aircrafts. There are like a minimum turning radius and sensing of ground-based targets, which requires the footprint for a downward-looking sensors to pass over a group of targets. Next slide, please. Yep. So here in this diagram, you can see a schematic of 3 target sensing problem. The goal of the path planning is to reduce the amount of time it takes to see all the targets. The research provides a path planning system for detecting a collection of objects in close proximity that fully exploits the sensor footprints planning flexibility while functioning with the aircraft dynamic restrictions. In this image, we can see 3 targets in the path, and a path plane target is to find optimal path between one point to another. For multi-targets, the approach involves in finding optimal path from the starting position to the first target, and then from the first target to the second targets, and so on until it reaches all the targets in their path. So there are 3 challenges that need to be addressed for achieving this. There are coupling between path segments, utilization of sensor footprint, determination of viewing order of the targets. We are going to discuss these in detail in coming slides. Next slide, please. So coupling between the segments. This strategy works well if the targets are widely spread relative to the vehicle's turning capabilities, as long as the ideal visit sequence can be defined. If the objects are close together, coupling between the paths related to the vehicle's dynamic constraint might result in a bad composite path outcome. In the figure A, the best route to the first object is found. As the vehicle files around the first target, it directions put towards the bad position to see the second target. The second and third sessions of the route have a similar coupling. Even the target 2 and 3 are both in ideal in terms of their beginning position and direction. The composite path is clearly suboptimal. Whereas in figure B, we can see clearly that the path segment from the beginning location to the first target is longer than the first approach. But the vehicle can see other targets and can reach them in a minimal path length for viewing all of the other objects. So the second approach will give the optimal solution in the end. Next slide. So second one is utilization of sensors and sensor footprint and viewing order. Many of the downward-looking sensors used by UAVs such as SAR and LiDAR having large sensor footprint. Because of seeing a target often does not need flying directly over it. Most of the path planners directly flow over constraints and do not utilize these sensor footprints range and flexibility. So having a sensor with a significant footprint size is beneficial. Using these sensor footprints when viewing closely spaced targets, it will provide the efficient path for us. So view order is the other challenge, which is similar to traveling salesman problem. So path planning difficulties with a restricted run radius and a sensor footprint to exploit are included in this study. Because of the complexity of the problem, only constant altitude and constant velocity flying with a downward facing sensor will be considered in this study. A planner with the following capabilities is required for an efficient path planning strategy. for viewing close displaced objects from an UAV. These are the three things that must consist for getting a best optimal solution. Plans optimal or near optimal paths through multiple targets by overcoming the effect of coupling between path segments. Utilizing fully sensor footprints to view targets, thus eliminating the need to fly directly over them. Determines the viewing order of the targets, yielding minimal length paths. Yep. Next slide. Discrete step paths. A successful path planning algorithm should provide a path that is unconstrained endpoints or directions that make full use of the vehicle sensors and fulfill the vehicle's dynamic restrictions. They are constructed by connecting primitive turn and straight segments to create the flyable path, which can give several characteristics. A flyable path is an established line of travel or access with a designed route followed by airplanes in flying from one port to another port. So the choice of which primitive is to use at each step is driven by the sense of grouping of targets. Next slide. So here we can see in this slide, we can see a flyable path diagram, which are constructed by connecting primitive turns and straight segments. The path planner goal is to search the path tree for a branch that achieves the given goals in the lowest amount of time. It has a depth of 3 branches. Shorter step length boosts the resolution of the path tree, where deeper trees allows for longer pathways by expanding trees converge area. Herein we have a formula d of psi equal to ds by rt, where ds is the specified length of the primitive segment and rt is the minimal turning radius that give vehicle maximum heading change at each step. The configuration of the vehicle at a node given by the triplet p equal to x comma y comma psi, where x and y represent the interior position and psi is the heading of the vehicle measured from the north. The vector from the vehicle to the ith target is denoted as di, we can see in the diagram. Because step length and tree depth have a substantial impact on the speed of the path planning research and quality of the resultant path. Their importance will be explored further in the next session by my team. So my teammate will explain those things in the coming slides. Thank you.
So hello all, my name is Murali Krishna Bomsetti. So from here I'm going to continue this presentation. So LRT8 star research. This work applies the learning real-time A star algorithm in a novel way to learn which branch of a path tree best accomplishes the desired path planning objectives. The LRT star algorithms is chosen over the faster A star algorithm because the limiting factor on the performance of the path planner is a memory space is required by the store the expanded nodes. So here we are going to discuss about algorithm details in initial heuristic, terminating conditions, branch terminals, path tree size, and step size selection. So now we are going to discuss about algorithm details. The LRTA star algorithm itself is simple and elegant. Each node has heuristic estimate h of the remaining distance that must be traveled to complete the objectives. The search continues to move down the tree until either all the objectives are accomplished or the path becomes longer than the current best path. At this point, the search has learned the minimum length path that accomplishes the desired objectives. The LRTA star research algorithm is outlined in algorithm. So here we can see this is the algorithm one, where h total is the total heuristic change for the current run and count is the length of the current path. Best count is the length of the best path found thus far and all sensed indicates whether all the targets have been sensed. In other words, when h star naught minus h naught is equal to 0, then such has found the optimal path for the root node to the child nodes. So next about initial heuristic. The primary requirement of LRT search is that HI is always true for any node of I. If a node on the optimal path overestimates the distance to the goal, the search may never move to that. Heuristics in tree search problem are estimates of the distance that must be traveled from current node to the completing the remaining task. The simplest method for calculating heuristic is to use the distance to the further target as the initial heuristic value, since we know the vehicle must travel at least that far to complete its objectives as shown in figure 7.3. So here you can see the figure 7.8 distance to the further remaining objective. Since it is impossible to determine when the path can be traversed, the initial heuristic value is calculated with this formula. These initial heuristic values are guaranteed to be admissible but not necessarily very close to the actual path length, and therefore the search may converge slowly. An alternative initial heuristic value is to find the distance to the target closest to the vehicle and then add to the distance to the target fullest from the first target as illustrated in uh, figure 7b. So here you can see figure 7b, distance to the nearest objective plus distance between the nearest and the farthest. To guarantee that the heuristic is admissible, one half of the sensor width is subtracted from the distance to the nearest target. The method here used is LRTA star algorithm and provides better path length estimates than the previous method. So next we are going to discuss about terminating conditions. The NILRTA star algorithm terminates when there is no improvement in path length. This condition is successful because the optimal path is typically found fairly quickly, and the majority of the search time is spent confirming that it is indeed the optimum path. The more iterations that are required, the better the resulting path links may be. But with increased running time, with the increased running time. Here in figure 8 shows the sample paths generated by LRTA and NILRTA star algorithms for the same test conditions. So in figure 8 here we can see the sample paths generated by the LRTA and NILRTA algorithms. So next we are going to discuss the branch terminals. So LRTA star tree search can be safely terminated when the path becomes longer than the present best path. If a node's children all have heuristic values of infinity, then the node is a dead end and it can be terminated similarly. Since the heuristic value of the node is always less than or equal to the actual path length, this can be used to cull nodes from the tree. So next is path tree size. A significant problem with searching the path tree is the size of the tree, the full size of the tree. The full path has a size of 3D, where D is the number of levels in the tree, and there are approximately 3.1 x 1014 nodes for a tree with 30 levels. Pruning the tree in this manner is particularly helpful when using small step size. For larger step size, it is permissible to allow the turn direction to change between segments, and thus full path tree may be used. LRTS.tree search is initialized using the results of a single source potential field path planning algorithm. Although the resulting path is suboptimal, this method reliability produces a feasible initial path for LRTS star algorithm. Additional goals and constraints can easily be imposed on the path. Such constraints may include viewing a target from a specific heading or range of headings. The LRTS star planner could be augmented with reactive capabilities to detect and avoid unknown obstacles that are sensed during the flight. Simple Dublin's path can form the basics for real-time avoidance maneuvers that would momentarily take the vehicle off the path and to avoid the obstacle. Implementing the additional goals and constraints is simply a matter of identifying and pruning infeasible branches during the tree search. An example of tree structure with a two-step look back is shown in figure 9. So here, this is a tree with two-step. Next is step size selection. The LRTS tree search is guaranteed to find the minimum length path from the discrete step path tree. The path is not necessarily the global optimal path, but a discrete approximation of the optimal path. In practice, this is not possible as the tree size would be too large to search effectively. Larger step sizes generally improve the running time of the algorithm with only a slight increase in the resulting path length. Next, we are going to discuss about testing and comparison. The LRTS star and NILRTS star tree search algorithms were tested on a set of 2000 target scenarios. The tests were conducted using an Athlon XP 500 Plus with 512 MB RAM and using the Linux operating. It can be shown that increasing the step size significantly reduces the running time of the algorithm with only a moderate increase in the resulting path lengths. So in this, we are going to discuss about LRTS research validation, path length, running times, and differing number of targets. So LRTA research validation. LRTA research algorithm can both utilize the full sensor footprint and learn the viewing order of the targets. Figure 10a shows that path generated by LRTS star algorithm is only 5% longer, resetting the sensor to its original dimensions produced by the path shown in figure 10b. Then the path found through the brute force global search based on Dublin's path. This path is 33% shorter than one that is upstream to pass directly over the target points. So next is path length. Path length performed for two algorithms at various step sizes is presented in figure 11. So this is the path length performance. The mean path length increases approximately 19% over the range of step sizes, indicating that smaller step sizes are better. At a step size of 0.5 radians, the algorithm switching to searching the full path tree instead of simplified path tree. So next is running times. So running times for LRTS star and NIL RTS star algorithms are shown in figure 12. So here you can see it figure 12. Running times are defined by the number of nodes that are visited by the search. At step sizes of 0.4 radians and above, two algorithms perform similarly. The result shows that increasing the step size improves the running time without significantly decreasing the path length performance. Next is differing number of targets. 2000 random target scenarios are used for each number of targets between 1 and 8. The running time results in figure 13a shows that running time for both LRTA and NLRT algorithm increase the size of the targets. So here you can see figure 13A and 13B. And figure 13B has path length performance comparable to the LRTS or algorithms. So here figure 14 shows an example of path generated by LRT algorithm for an 8 target scenario. A video of simulated UAV flight over the 8 targets can be viewed by clicking. So conclusion. This work presents that LRTS star and NLRTS star tree search algorithms, which find the branch from a discrete step path tree that best accomplishes a set of desired objectives. The algorithms plan optimal paths through multiple targets by overcoming the effects of coupling between path segments. They fully utilize the sensor footprint to view targets and eliminate the need to fly directly over them. So that's it about this research paper. Next, my teammate will continue.
Hello everyone, I'm Pratima Samineni. So today I'm going to explain about the second paper, which is based on KNN LRTS star search. So coming to the abstract part of this paper, so the real-time search algorithms are used to make the optimal decision to find the solution. So what the example for this real-time search algorithms or LRTS search, these algorithms are also used to solve larger problems than heuristic evaluation functions. On the other side of this, these uses running approaches that frequently result in low solution quality and make the agent appear illogical by repeating the same steps. This problem is overcome by a new algorithm known as DLRTA star, which eliminates the learning by selecting the few subgoals. So here I have discussed about the heuristic evaluation. What exactly it is it is a fundamental problem solving method in artificial intelligence, and the performance of such algorithms is greatly improved using this evaluation function. A heuristic evaluator is a function that is inexpensive to compute and estimates the relative merits of different states related to the goal. There are few issues with this LRTS star search, and that it requires an enormous amount of memory to do the function. And also the creation of the subgoal database can take up to 70 times as much memory as the map itself. During the pre-computation phase, the LRTS search creates a database of subgoals. Compared to most of the video games, the new algorithm uses nearly 9 times less memory than the DLRTS search. Well, coming to the next slide, which is an introduction part of the presentation. To discuss about the agents in the artificial intelligence, they will react quickly to the player's commands and also to other commands also. Real-time operations are distinguished by the requirement that an agent plan and execute actions in a consistent time interval that is independent of the size of the problem being handled. For example, there are few static search algorithms which cannot guarantee a constant bound on planning time per action, like A star, IDA star, and ARA star and AD star. Their planning time will certainly expand as the problem grows, exceeding any predetermined limits. The search algorithm DLRTS star analyzes a state space and computes a database of subgoals in its pre-processing space, as I discussed earlier. And also it had few memory requirements and complex pre-processing modules. For example, the database need up to 70 times as much memory as the map for which it was designed while pathfinding on video game maps. And database was loaded in its entirely into the random access memory. The new algorithm named KNN LRTA star, where KNN is a and which follows lazy learning idea, builds a database of subgoals instead of analyzing a map and building click-based abstraction. By essentially eliminating the learning process, the best results were produced. This can be accomplished by computing heuristics with respect to a close-by subgoal rather than a far-off goal. Here in the next slide, we can observe from this diagram, we are having a 4 parts A, B, C, and D. So from the above diagram A, there is a graph is generated by converting the grid-based map. In the second diagram, it is subsequently abstracted into a single abstract state for each click of the original states. And from the third diagram, it has been shown that the abstraction is completed, then the center of the click is taken as a representative of the abstract state. And the last, from the fourth diagram, it has been stated that it represents all the representatives are marked with the white circles. So this is all about this diagram. And we're coming to the next slide, which is a subgoal database construction. So this is an algorithm which is used to find the subgoal database. So most of the memory consuming part of DLRTS star lies within this subgoal database. This search algorithm abstracts the map with the help of click-based abstraction scheme of PRA star to build the database. DLRTS star considers all pairs of abstract states once the map is partitioning into regions. For each pair, the search algorithm DLRTS star finds an optimal path. It makes the ground level state by tracing the path from the start representative. Here are the few memory requirements, where V is the number of ground level states and V is the number of abstract states of an abstraction level. They find the simple way of creating a subgoal database by following few approaches. Yeah. So we're coming to the next slide, which is a runtime search. Sometimes the state of the agent and its goal will not be in the database. Like on the other side, the agents will look into its records if it is unable to find the exact goal. So the simplest mechanism for runtime generation is a KNN, which is a K nearest neighbor. So this is an approach used for subgoal selection and for also the simplicity. Thus the similarity is defined by finding the distance between the S start and S hyphen start and these. So once the agent has found the database record that most closely resembles its current state, it sets the subgoal from that record as its own subgoal and uses the normal LRTS star to get there. Second, despite the fact that subgoal, by design, the subgoal is hill climbing reachable from S start. So what exactly the K nearest neighbor algorithm is? It is a supervised learning method that is non-parametric. The function is only approximated locally in KNN classification, and all computation is postponed until the function is evaluated. A KNN is also defined as a lazy algorithm, which implies that instead of running a distinctive function from the training data, it memorizes it. The heuristic values in the other states are then compared to discover the type of state that is most like the current state to a depth of K. The KNN LRTS star search algorithm then jumps to the state and uses a hill climb method to repeat the procedure. There are few issues to address this search algorithm. Coming to the first issue, the global goal may be accessible by hill climbing from the agent current condition, but the agent may choose a sub-goal that leads it away from the goal. And the second issue is, although the sub-goal is hill climbing reachable by construction from S start, this is not always the case from the agent's actual state S start. But coming to the third issue, the possibility of cycles is the third issue. It's possible that the agent achieves its selected goal sub-goal and then sets the following sub-goal to return it. And the last issue, the similarity metric ignores obstructions because it is based on a octile distance. As a result, the most similar record may find upon the other side of an impediment, requiring the agent to spend a significant amount of time navigating around it. So this is all about the runtime search. While coming to the next slide, which is an empirical evaluation, we can see in the diagram, the first diagram is mean database size, and you can also call it as a map size. And the second diagram is a mean number of states expanded per move. They used 8 maps for popular video games for the empirical evaluation. From these 8 maps, they ran nearly 128 different pathfinding problems instances on each map. Each data point represents on an average of 1 or 2 for separate pathfinding searches. That is 8 maps, each with 128 searches. So this diagram represents the empirical results. The figures 2 subrows depict the suboptimality of courses taken by agents controlled by DLRTS search algorithm or KNN LRTS search algorithm. From the first diagram has been observed that the suboptimality as a function of the database size is depicted. And from the right plot, the suboptimality is depicted as a function of the number of states expanded in every move. So we're coming to the conclusion part. The main motive is to build a real-time algorithm for pathfinding in video games by minimizing the memory requirements of the DLRTS search algorithm. The above problem is solved by another new algorithm called as a KNN LRTS search, and it also provides good runtime real-time performance. With the use of DLRTS algorithm, it requires less memory for sorting the sub-goal database. In terms of future development, we believe that KNN LRTA algorithm can be improved further to meet the DLRTA runtime performance completely. So this paper is all about the comparison between the DLRTA search algorithm and KNN search algorithm. And it has been observed that the KNN LRTA is the best algorithm to find the pathfinding in video games. So this is all about our presentation. Thank you.
Thank you all.
Thank you.